Okay. Okay, so let's get going. I want to start with a few announcements. One of them is that there's a homework due today. Homework number 4. It's on flow graphs. Please hand it in at the beginning of the lecture. Pick up the solutions to that on your way out. There's also the first lab assignment of the semester that you're going to be doing. It's here. Let me take one example of it. It's not off of Oppenheimer and Schaefer. It's off of a different book, which because I don't want you to pay another $60 or so to buy the book, we just made a copy of some of the pages. The way this handout is organized is there's a lot more material than you need to do. What you need to do is places where it says question 1, question 2, question 3, and then question 4, question 5, and question 6. The parts, so specifically we're saying what 6 questions out of this you have to do. Because we Xerox copied it, we didn't do sort of cut and pasting to be able to do that. That's due next Friday. It's a lab assignment and it uses MATLAB. So for those of you who have not used MATLAB before or rusty or forgot how MATLAB works, or in general, I would encourage you to get started on it early. I guess the other announcement is that midterm is still scheduled for October 22nd. And what material will be in it we'll discuss later. Just so that you know, you can bring one sheet of formulas or equations or whatever you want to bring to the exam, two-sided, and you can write as small as you want on it if you want to. Just so that you don't have to memorize equations and things like that. And it'll be an hour and a half, and it'll be at the same time as the classes. The only thing is that it could be that it might be here or it might be in Sibley Auditorium. I'll let you know later. But the time is for sure Wednesday, October 22nd, 9:30 to 11. Okay. So you might want to, if you have questions, that's not where the homework gets handed in. It's over there. If you have questions on how to do the MATLAB stuff, you might want to go talk to Dan Hazen during his office hours and get help in sort of getting started with MATLAB. If Dan ends up having his office hours in the computer room, he'll put a sign saying, okay, my office hours this week is held in whatever, 119 Corey or whatever the machines are. But I'll ask him to do that if he ends up doing it in that lab room. Any questions? Okay, so don't forget to pick up the lab assignment on your way out. So what I'm going to talk about today is wrap up the discussion on FIR linear phase type filters, and then talk a little bit about quantization stuff and what effect the quantization of filter coefficients have on the frequency response, and what effect does the realization of the filter that you end up having will have on the, together with the quantization of the coefficients have on the final frequency response. And then after that, I'm going to change gears and start talking about filter design. We'll start with FIR filter design and then move on to IIR filter designs. Okay? So just a brief overview of last time's lecture. Actually, let me put the mic on. I still haven't done that. Okay. Just to do a quick overview of last time's lecture, so could you bring in the camera? So we showed two things. We started off by showing that if you impose this kind of a symmetry condition on the filter type coefficients of an FIR filter, then you end up having linear phase. And we spent a bunch of times deriving that. I won't go over that again. And we found out in the process of doing that alpha, if this is the linear phase filter, alpha is the slope of the phase as a function of omega. Alpha is n minus 1 over 2, where n is the number of taps in the filter. And then we sort of reversed, and then we ended up showing that, look, if you have linear phase filters like that, the convolution process becomes half as expensive. In particular, we end up having half as many multiplies, and this is the sort of the flow graph that we end up getting. Then we turned things around and said, okay, instead of assuming symmetry and showing that the thing is linear phase, why can't we solve it in a more general form and find all the other conditions under which the filter becomes linear phase? And we came up with this equation saying that if this equation is satisfied, this is a necessary condition for having generalized linear phase. And we considered two cases of it. Beta, which is, if you recall, if this is the form of our generalized linear phase, beta is where this line, the angle of h of omega, intersects the vertical axis. So we came up with this equation, and it's still difficult to know under what conditions you get linear phase. And the answer was, if beta is pi over 2, or 3 pi over 2, then an anti-symmetric condition like this will make the thing be linear phase. And if beta is 0 or pi, then a symmetric condition, which is h of n equals h of 2 alpha minus n, results in this fancy equation here to be satisfied. And then I showed you a couple of examples of it. So we have essentially two cases: beta 0 pi versus beta pi over 2 or 3 pi over 2. And then what we ended up the lecture was that, depending upon if the number of taps is even or odd in each of these two cases, you get 4 different types of filters: type 1, type 2, type 3, type 4. And in particular, this is sort of the end of last time's lecture. Type 1 is when you have symmetry condition and number of taps is odd. Type 2 is when you have symmetry condition, number of taps is even. Type 3 is when you have anti-symmetric condition, number of taps odd, and type 4 is anti-symmetric and number of taps even. So I'm going to just wrap up that discussion in the next 5 or 10 minutes, and then talk a little bit about quantization stuff. So what I'm going to do is just draw a little table where we put in these 4 types of filters. And what I'm basically trying to do is deduce, where we ended up last time's lecture was these 4 types of filters. Some of them, for example, type 3, you could show that value of h of omega at omega equals 0 is always 0, and h of omega at omega equals pi is always 0. So what we discussed last time was some of these filters cannot be used to design, for example, low-pass filters. A low-pass filter ought to pass the DC and low frequencies, and if let's say type 3, no matter what the filter coefficients are, if it always happens that it doesn't pass DC, its frequency response at DC is equal to 0, it cannot be used for low-pass filters. So that's sort of the purpose of this little table that I'm drawing right now. Okay, so we're going to have maybe 4 lines here. I'm going to talk about the symmetry condition. I'm going to talk about n, which is the number of taps. And I'm going to talk about alpha, the beta that they take, and then H sub m of omega. And then the last column is the constraint on that filter. And the rows of this thing are going to be type 1, type 2, type 3, and type 4. Okay, so as I just said a minute ago, type 1 and type 2 are symmetric, so h of n is equal to h of n minus 1 minus n. H of n is equal to h of n minus 1 minus n. Type 3 and type 4 are antisymmetric, so h of n is equal to minus h of n minus 1 minus n, and h of n is equal to minus h of n minus 1 minus n. And the number of taps, as I said earlier, for type 1 is odd, for type 2 it's even, for type 3 is odd, and type 4 is even. That's the way we define this. Alpha is always n minus 1 over 2, regardless of what situation you're in. Okay. And beta, for these two, were equal to 0 or pi, it doesn't matter. And for these two, was equal to pi over 2. So 0, 0, pi over 2, pi over 2. So far you've seen everything before, but what I didn't get a chance to talk about last time is this expression for h sub m of omega. Remember, what is h sub m of omega? Well, if we define, just as a reminder, a generalized linear phase filter, then h of omega is equal to some h sub m of omega times e to the minus j. Let me make my definition precise, beta minus alpha omega. So this thing was the thing that we called real. Okay. So this h sub m of omega, in this situation, you can show it's given by the following summation. Summation from 0 to n minus 1 over 2, a of n cosine omega n. And note that because n is odd, n minus 1 is even, and therefore n minus 1 over 2 is an integer, so this thing makes sense. Where a's are some coefficients related to these real coefficients h's. Okay. And then in the second case, in type 2, this thing is equal to summation from n equals 1 to n over 2. And again, n is even, so I can talk about n over 2. B of n cosine of omega n minus a half. And type 3, we got summation from n equals 1 to n minus 1 over 2. C of n sine omega n. And type 4, you got summation from n equals 1 to n over 2, d of n sine omega n minus a half. So looking at these, then why did I write these h sub m of omegas? Well, because I wanted to see what kind of constraints they satisfy. So this one, I'm sorry, the constraint that I'm talking about is h sub m of omega times e to the j beta. What is this quantity? Okay, so given that this is h sub m of omega is real, and in this case beta is equal to 0, in this case h sub m of omega times e to the j beta is just real, and that's about the only thing we can say about it. In this case beta is equal to 0, so we can still say that h sub m omega e to the j beta is real. But we can say one more thing here. If you plug in pi at omega, if you plug in pi into this thing, you'll find out that the frequency response at pi is equal to 0. Okay. And therefore, one conclusion that you can get from that is that we cannot use this type 2 to be a what? What kind of filter can it not be? a high-pass filter. And I'll elaborate that in just a second. H sub m of omega e to the j beta, when beta is pi over 2, e to the j beta is j, and therefore j times something real becomes purely imaginary. I mean, but then another consequence is that if you let omega equals 0 or omega equals pi, this whole thing becomes 0. So h of 0 is 0, and h of pi is equal to 0. And finally, in type 4, beta is still pi over 2, so it's purely imaginary. And you can see that if omega is equal to 0, this becomes 0. So h of 0 is equal to 0. So this can't be a low-pass filter. Okay? And let me just give you a little bit of a hint as to where you can find in Oppenheimer and Schaefer where the discussion on these type 1, type 2, and linear phase type things is. It's essentially, it's essentially section 5.7 of Oppenheimer-Schaefer that talks about linear phase, then general types linear phase, and then the 4 types of linear phases. So it's from page 291 to 311, in case you want to do some reading. Because the reason I say that is because we're jumping around a little bit. We're in the midst of chapter 6 now. I've sort of come back and covered part of chapter 7. So in case you're reading this stuff, that's where it is. Now, I would like to also talk about the 4 classes of filters, low pass, high pass, band pass, and band stop, and then make another chart explaining which one of these types can be used with which classes of filters. We've talked about it just a little bit. So let me talk about that for just a second. So there's could you bring the camera down just now? Thank you. So there's 4 classes of filters that in general one deals with. The first one, and perhaps the one that's most commonly used, is low pass filter, where magnitude of h of omega as a function of omega looks something like that. And because I'm assuming real coefficients, then magnitude of h of omega is symmetric, and therefore I only worry about between 0 and pi. 0 and minus pi, it's the same thing. So that's an example of a low-pass filter. Okay, and this is called like the cutoff frequency. Then the other type of filter people worry about is what's called high-pass filter, where it's 0, and then it goes up at some value, so h of omega. And then the third class is bandpass filter. H of omega as a function of omega. Where you're passing a specific band and you're not passing other bands. And then the fourth class is what's called band stop filters. When you're looking at magnitude of h of omega as a function of omega, and you pass every frequency except for some other ones, like here. Okay, so what would be an application where you use low-pass filter? Essentially to get rid of noise. Noise is typically always high frequency and it corrupts your signal, and you want to get rid of it, so you pass the signal of interest, the signal that carries information or whatever is occupying mostly the low frequency band, so you design a filter to keep that and get rid of the other ones. What's an example of a situation where you want to do high pass filtering? Like an image pass. Pun?
Get rid of offset.
Yeah, get rid of some offset. In image processing applications, you might want to be sharpening something or coming up with an edge detection where you only see the high frequency components of an image to know where the sharp edges are. That's an example of a high pass filter. Band pass filter. That filter is used a lot. What's an example of that? Yeah. Your tuner, you're essentially trying to tune in to a particular range of frequencies. And how about band stop filter? What's an example of that? These are situations where you want to get rid of one specific frequency that's bothering you. Like in real life, what would it be? And look where I'm looking at. Yeah, like the 60 hertz, which is the AC frequency of the power lines. It comes in, it messes up a whole lot of other signals inadvertently, unintentionally, and you want to be designing what's called a notch filter to get rid of, let's say, 60 hertz or some other thing. So that's an example of band stop filter. Now, looking at this list of filters here, what can we say about the applicability of these type 1, type 2, type 3, type 4s to these 4 classes? Look at type 1. Does it have any constraints? Not really. So it can potentially be used in all 4 classes. So type 1, type 1, type 1, type 1 can be used in all of these. And as you'll see, a lot of times to simplify our lives, we use type 1 because it doesn't have any of these things. Type 2, h of pi is equal to 0. That means right here it goes through 0. So can it be used for the low pass? Yeah. Can it be used for the high pass? No. Can we use for this? Yeah. Can we use for the band pass? So can it be used for this? Yes. So let's just add type 2. Sorry. And can it be used for band stop? No, because at pi it goes to 0. So type 2 can be used for low pass and band pass, but not the other 2. Type 3 has even more constraints. At 0 is equal to 0 and at pi is equal to 0. So it can't be used here. It can be used here. It can be used here because at omega equals 0, this cannot be 0 if it is a low pass. It can be used here because at pi it's 0 and it shouldn't be. It could be used here, so type 3. And it can't be used here because at pi it's not equal to 0, nor is it omega equals 0. And finally, type 4, if you stare at it, it says h of 0 is equal to 0. So it can't be used here. It could be used here, so type 4. It could be used here, and it can't be used here. So there's the lesson to learn from here is type 1 can be used for all kinds of filters. So that's sort of the most general one because it doesn't really have much bad things sort of going for it. So if I were to convert this picture into yet another table, I would get the following thing. So here's yet another table. Okay, so I have low pass, high pass, band pass, and band stop. And I have type 1, type 2, type 3, and type 4. And again, looking at here, low pass I can have type 1 and 2. Type 1 and type 2. But I can't have type 3 and type 4. High pass I can have 1 and 4. So 1 and 4, and not these 2 other guys. And band pass, I can have all 4, so I can put a check mark on all of them. And band stop, I can have just type 1. So type 1, and none of these. Okay? Of course, this classifications of the filters I've done is pretty naive and simple, but it does get us somewhere. Not all filters fall into these 4 categories. For example, if I have a filter h of omega that that does all kinds of funny things like that between 0 and pi. It's none of those. It's not low pass. It's not band pass. It's not So what we've talked about now is these four things is sort of a bit of an oversimplification, but it accounts for 99% of all the filters that people typically implement in practice. Okay. So I'm going to pause right here and say a few words about quantization stuff while you have the flow graph things fresh in your mind and haven't quite forgotten about how the thing works and what the issues are. And then move on to, I think, chapter 7 of the book. I think it's 7, but whatever chapter that talks about filter design, FIR filter design, and IIR filter design. Okay? All right, so let's say a few words about quantization stuff, as I promised I would do. Okay, so the first thing that you have to worry about in any sort of real life situation is that there is no such thing as infinite precision. Okay, this concept of real numbers and it doesn't exist when you go into implementation. Everything has a finite amount of precision. So so the first concept is that in implementing things, you have what's called finite precision. Yeah, and what do I mean by finite precision? Well, if you have finite precision when you use an A to D to quantize the signal, you have finite precision when you represent your FIR or IIR filter coefficients. You don't represent them with the real numbers. And you also have finite precision when you add things up and multiply things up. If you have an 8-bit number and another 8-bit number, multiply them, you get 16-bit number, and then multiply it again by another 8-bit number, you get 24-bit numbers. You can't allow the precision to just grow unboundedly. You've got to make up your mind what the precision for the system is, and you have to stick to it. So what I mean by finite precision, I mean when you do in three cases: A to D conversion, you get finitely many bits per sample, finite number of bits of your signal per sample. Number two, when you do coefficient quantization in your filter implementation, you can't be representing it with infinite precision. It has finitely many bits. And then finally, when you add, when you implement, let's say, a flow graph, the arithmetic can't have infinite precision. Arithmetic, it has finite precision. Okay. And so, bottom line is you have to come up with a number representation scheme. So you have to come up. We need a representation, a finite precision representation for our numbers. Representation scheme for finite precision. And there's many possible representations. There's one's complement, there's two complements, and many other ones. But the one that we'll talk about in this lecture today is two's complement. So we represent real numbers in two's complements, and I'll explain what that is in just a second. So real numbers have infinite precision. By the time we go to two's complement, we have finite precision. And what do I mean by that? If I take a real number x, then I can write it as some x sub m minus b naught plus summation from I equal 1 to infinity of b sub I 2 to the power of minus I. Okay? And what are these various pieces? Where x sub m is some sort of a scale factor. In particular, we're assuming that magnitude of x is bounded by x sub m. This is how big you assume your numbers are going to ever become. That's the largest number in your representation. Let's say you've done your analysis and you're designing a filter and you know what the amplitude of your signals is and you know what the coefficients are doing, and you decide that no number is going to exceed, I don't know, 16,000. Okay? And why is that important to have this scaling factor? Why is it important to know what the largest number is you're going to have in your system? Because when you add things up, there's a possibility of overflow, for example. And so it's important to make this number large enough such that you avoid overflow. Or if there is possibility of overflow, you scale things ahead of time properly so that you don't overflow. Okay, so that's sort of the maximum value. B naught is just the sign bit. It's either 0 or 1. In particular, if b naught is equal to 0, then x is negative. If b naught is equal to 1, then the other way. So x is positive, and if x is negative. So that's just a convention for representing that. And these BIs are either 0 or 1. That's the thing that represents what your number is. Okay. So if you have right now the way I've written a real number, it has infinite precision because the number of BIs are infinite. I ranges from 1 to infinity. So the more BIs I add, the more precision I get. So I can have, because I can go all the way to infinity, I'm adding lots and lots and lots of precision. This is a real number between 0 and 1? Yeah. No, the x of m makes it not 1. This is a real number between 0 and 1 times x of m. So that's why x is between magnitude of x smaller than x of m. That's what I mean by this is scaling factor. This is bounded by 1, and this x of m makes the whole thing bounded by x of m. Okay? It's an arbitrary scaling factor at this point. Okay, so this is with infinite precision. Now, what if I insist on having finite number of bits? So we want finite number of bits. In this case, I say b plus 1 bits. And if we do that, we get the following. The quantized version of x, which I call x hat, is quantized with b bits of x, is given by x sub m. It's the same thing, but I'm just not going to let this thing go to infinity. I'm going to stop at b. It's minus b naught plus summation I from 1 to b of b sub I 2 to the minus I. Okay? And this is equal to, so this x hat is just a quantized version of x. This is equal to also xm times what I call x hat of b, where this thing is just, by definition, x hat of b. Okay? So x hat of b is again the quantity that's between 0 and 1. Does everybody see why this is between 0 and 1? It's sum of powers of 2 to the minus 1. It's sum of powers of a half. When I is equal to 1, you get b sub I times half. Yeah, it's b sub 1 times half, plus b sub 2 times a quarter, plus b sub 3 times an eighth, plus b sub 4 times a 16th. So you're adding powers of 1/2, and so this is always smaller than 1, and this is just a sign bit.
You never actually get 1.
No. No, you don't. Yeah.
What do we have b plus 1 bits?
Well, there's b bits here, and then the sign. You have to represent it. The thing is positive or negative. Otherwise, there's going to be ambiguities. Okay? So if I do that, so essentially x hat is just a quantized, I wrote that already here, but I'm going to say it is say it again, it's a quantized version of x. And what can we say about the smallest difference between two numbers? In this number representation schemes, what's the smallest difference between two numbers?
2 to the capital B.
That's right. So smallest difference between two numbers here is 2 to the minus b, but then you have this x of m scaling factor, so you multiply by that. So the smallest difference between the numbers is 2 to the minus b times x sub m. And I define that as being delta. I'm off screen. Okay? And in this case, the quantization range x hat, once again, is magnitude of x hat is also x sub m. That means x hat is between plus x sub m and minus x sub m. And finally, I can write this this x hat of b, which is the fractional part of these, without getting multiplied by the scaling factor. I'm going to write that as a binary expansion in the following form. So I'm going to write x hat of b as in the following form: b naught, and then this is not the decimal point but the binary point. Okay, the b1, b2, all the way b sub b. Okay, so this is the representation of this number. So this tells me whether it's positive or negative, and this tells me, so this is b1 times a half plus b2 times a quarter, plus b sub b times to the minus b, and then multiply by x of m, and that tells me the quantization, the value of, the quantized value of x. And b naught tells me whether it's positive or negative. Okay. So how do I, so this is just a representation of a finite precision number, but if I have a real number, let's say 5.68932, how do I end up coming up with this binary representation? This 2's complement, this is just a, 2's complement is just a way of representing numbers in binary form, but how do I convert a real number to something like this? Well, I can either round or I can quantize, right? I mean, essentially, so, and I'll show you what I mean by each one of those two things. So what I'm trying to say here is that if you start with a real number, then you can quantize it either by rounding or by truncation. And you all know what we mean in the decimal world, the decimal number representation, what we mean by rounding and quantization. Let's say I have a number like 5.69, and I want to round it to 2 digits. What's the rounding? 5.7, right? You get it. And the same number, 5.69, but I want to truncate it to 2 digits. What do I get? 5.6. So the same idea holds true here. So both rounding and quantization, it turns out, are nonlinear memoryless operations. So rounding and truncation, they're both nonlinear, and they're both memoryless operations. And what do I mean by nonlinear? The same meaning as linear as we talked about. That means if I either round or quantize a number, number 1, and then round and quantize another number, and I add those two either rounded or quantized numbers, I get a different thing that if I were to quantize, if I first add them and then round them. That's what nonlinear means. I don't always get the same answer, right? It's the same concept of linearity as we talked about earlier. It also means if I get a number, quantize it, then I scale the number and then quantize it. The quantized number I get is not the scale value of the quantized thing before. So it's not linear. And it's memoryless. That means that if you have a system that has a sequence of numbers coming in, it doesn't keep track of what the previous state was or what it did to the previous number. It just does it. So what is the, how does, in the binary world or something like that, how does rounding and truncation work? Well, if you can zoom in here. So this is if you have just a capital B equals 2, right? That means you have a B naught, which is the sign term, and then we have B1 and B2, just 2 bits to represent our numbers. So you have 4 positive and 4 negative ones, and these are shown here. And this is the input-output. This is on the x-axis is x, and on the y-axis is quantized value of x. And what happens is, this is what you get when you do rounding. All the numbers between, let's see, plus 1/8 and minus 1/8 are rounded to 0. Between 1/8 and 3/8 are rounded to 1/4, and the same thing with the negative. 3/8 and 5/8 to 1/2, and 5/8 to, I think, 7/8 are rounded to 3/4. Okay? In contrast, that's what you get when you truncate. All the numbers between 0 and 1/4 get mapped into 0. 1/4 and 1/2 to 1/4, 1/2 and 1/3 to 1/2, and 3/4 and 1 to 3/4. And if you now zoom out so people can see both simultaneously, you can see that when you do rounding, the dead zone or the 0 lies halfway in between. When you do truncating, the dead zone is to the right. Right? That's the artifact of truncating. And there is a thing that you can talk about which is called quantization error. Quantization error is Q of x minus x. How much error did I endure when I did this type of a quantization, or this kind of, in this case, rounding, and in this case, truncation? And what is the quantization error when you're doing rounding? Between what and what values is it? Yeah, let's talk about it in terms of delta. Delta is the smallest difference between the two numbers. In this case, delta is 1/4, for example, right? So, so in terms of delta, what range is this quantization error taking? Delta over 2, or it may the error can be in a range. Sometimes the error is 0. If the input is 0, the error is 0, right? If the input is exactly halfway in between, I mean, the way you do is you just draw a straight line and you compute the difference. Sometimes, depending upon what the input is, there's no quantization error. But I'm asking, what is the range of quantization error? 0 to delta over 2 is one answer. It's from minus delta over 2 to plus delta over 2. So what is it? How many people think it's minus delta over 2 to plus delta over 2 in this case?
Well, you consider the absolute value.
No, I'm talking about not absolute value, just... So it is between minus delta over 2 and plus delta over 2. Why? Well, because let's consider the range between like 1/8 and 3/8, right? If you're 1/8, you have a lot of error. If you have a 3/8, you have a lot of error, but on the 3/8, you have 1/8. Between 1/8 and 3/8, you get to quantize 1/4. So when you're at 3/8, you're off by 1/8. When you're at 1/8, you're also off by 1/8, but the other direction. So both 1/8 and 3/8 get quantized to 1/4. So it's either minus delta. It's anywhere between minus delta over 2 to delta over 2, right? Now come down here. What's the error in this case? Again, zoom in one more time. So delta is still, 1/4. What's the error range? it's 0 to delta. Again, consider 1/4 to 1/2. When it's 0, I'm sorry, when you have 1/4, you're right on. You've truncating 1/4 to 1/4 just gives you no errors at all. But when you have 1/2, then you're off by a quarter, which is exactly what delta was. So it's between 0 and delta. Okay, so let's write that down. So if you can zoom in again. So if I want to define error to be the quantized value of x minus x, then for 2's complements, which is what I'm talking about, when I do rounding, then the error is between delta over 2 and minus delta over 2. And when I do truncation, the error is between 0 and delta. Okay? All right, so what's the big deal about all of these things? Well, the big deal is we want to do arithmetic with these things, and when you do arithmetic, the thing that could go wrong is really overflow. Okay? So what do I mean by overflow? Well, suppose I'm dealing with 2's complements, and I'm dealing with 4 bits total. So 3 bits of numbers plus a sign bit. Okay? And so I have a number like 7. What's the representation of it in 2's complement? Well, it's 0 because it's positive, and then 1, 1, 1 because that's how I have 7. And then I want to add it to another number, which is 1. What's the 2's complement representation of 1? It's 0, 0, 0, 1. This 0, again, is a sign bit. Let me just emphasize it. That's the sign bit, and this is the 1. And it's not too hard to see that when I add these two things, if I just do normal fixed point arithmetic, I get 1, 0, 0, 0, because this just got carried over. And in 2's complement, what does this number represent? Not 8, but minus 8. This is a negative sign, and these are 0, 0, 0s. Okay? So this corresponds to minus 8. And so we're sort of in trouble. You added 7 and 1, and you got minus 8. And in particular, if you keep just not paying attention to overflows and just add numbers like that, this is sort of the overflow situation that you're going to be getting. So this is, if you can zoom in, so this is your number representation. So instead of getting 8, which was the next number over, you overflew and came all the way back down. So you get this kind of a problem. And so this is called natural overflow. An alternative is to detect that you're overflowing when you're adding two numbers, and you say, I'm just going to saturate. I'm just not going to let the thing go beyond a certain level. And of course, both of these approaches have pros and cons, and when you're designing systems and you're designing algorithms that have to be implemented in finite precision and you worry about overflow, basically you can take one of the following two approaches to deal with overflow. One approach is deterministic. Ahead of time, you just, at each stage, you estimate or you predict or you come up with a guaranteed bound as to what is the largest value this register, this quantity, this variable can ever take, and therefore design your whole system so that you never overflow. That's one approach. And what's the difficulty of this approach that I just talked about? Yeah. What value these registers and these variables take are highly dependent on what input comes. And what input comes to you is highly dependent on a lot of things. It depends what I just said today. If I yelled and screamed, my input is loud and your thing will overflow. And if I just talk in a low voice, your thing will never overflow. And you're designing systems with signals that you don't know what the input to it is. I mean, if you knew what the input is, why have a system? You just know the answer ahead of time, right? You don't need to compute it. Yeah.
Can you mention that 1, 0, 0, 0?
Mm-hmm.
Why is that negative 8? Why is that not negative 0?
because, well, it's negative because B0 is 1. And then B1, B2, and B3 are all 0.
Yeah.
So this would be, so let's just plug it into this. B0 is 1, and B2, B3, B4 are 0. So this thing is 0. So minus 1, and x of m was 8. So minus 1 times 8 is 8. Minus 8. So it follows straight off of that. Nothing really fancy. So, actually, I had noticed a lot of you were still thinking about that. That's a good thing you asked. So as I said, for God's sake, doesn't have to be FIR or IR filter, and this could be a really complicated video codec that has filtering, motion estimation, DCTs, quantization, a whole lot of junk in it. But for the whole system, so you get a bunch of pixels at the input each frame. You do motion compensation, and you do this, and you do that. There's like 10 stages the thing goes through. And if you're implementing in fixed point, which we are, and I can tell you on cell phones, we are implementing those on fixed point. There is no floating point arithmetic on the $49 cell phone that you buy, which runs an ARM 720 megahertz thing. There is no floating point there. When you do it in fixed point, you have to make sure at each scale, for all possible inputs, the thing doesn't overflow. Well, you don't know what the input is, but you have some idea what the input is. For example, if your video is 8 bits per pixel, then your range of values is between 0 and 256. So you can, based on that, you sit down and laboriously derive the maximum values each of these registers and variables can ever take, given the input is between this range. And a lot of times it's not very easy to come up with analytical terms or bounds as to how large these things get. So that's one way of doing it. Another way of doing it, and in video, by the way, or in images, when you don't do a good job of that, let's say your pixel value, at the end when you did all your computation, your decoder decoded everything, and instead of computing the output to be 256, it computed to be 257. You spit that on the display, and instead of having a really bright value, you get a really, really dark value. So this overflow thing I just said, you visually see it when you deal with images and videos and displays and all that. So unless you did a good job of estimating what these bounds are and either scaling things down ahead of time so you don't overflow, you're going to get stuck. So that's a deterministic way where you guarantee. But another approach is probabilistic way where you say, well, on average, I'm not going to get a situation where all my pixels are 256. That's ridiculous. If you wanted to do a deterministic kind of analysis, you end up with very, very pessimistic bounds, and you end up scaling things down unnecessarily, and it has negative consequences. So alternatively, you can do a probabilistic approach. You say, on average, the pixels are this, and therefore with probability 99%, I'm not going to hit an overflow. And if, or 99.99%, if once in a blue moon I do hit an overflow, that's okay, because the consequence of taking care of that and scaling down for that is so grave that I might as well, take that risk and once in a while have a little bit of an overflow, but not suffer the rest of the time. Okay. So essentially designing systems so they don't overflow is in converting. I mean, one of the tasks that DSP engineers always end up having to do is that when you develop algorithms for correctness, let's say you're doing a target recognition thing, right? Or when you're developing algorithm, you're all using MATLAB, which I'm guilty of using MATLAB too. I just gave you a MATLAB assignment. But nevertheless, it has infinite precision. It's nice and good. Your first order priority is, does this algorithm do what it's supposed to do? Does it track the target? Does it recognize the target? That's already a hard enough job. And then when you're all done doing that, the next step is just transform that floating point algorithm into fixed point and make sure it runs on available hardware that's available. Now, in some situations, you have the luxury of having fancy hardware, but in some situations, you have to deal with, $49 phones or something. So, how do we deal with, how does this overflow thing manifest itself in terms of trade-offs? Or inherently there's a trade-off between quantization error and dynamic range and the number of bits. So What do I mean by that? Well, to minimize overflow, suppose I keep my number of bits fixed at B. Let's say 10 bits is all I'm ever going to spend on each of my registers. If I want to minimize the possibility of overflow, what do I have to do in this system down here? I have to pick what? X of m to be large, right? Because if x of m is small, I quickly overflow and I'm done, and all the numbers are wrong. So if the number for a fixed number of bits here, to avoid overflow, I have to increase x of m. But if I increase x of m, then what's the downside of that? The error increases because we just talked about that. The smallest difference between them is 2 to the minus b x of m times delta. So if x of m goes up, delta goes up. And if delta goes up, the quantization error, which we just talked about, goes up. So you can either have really large x of m's and never overflow, but then have a large quantization error, or you can have small x of m and therefore small quantization error and have a large overflow. But the way to fix all of it, if you want to have both a good dynamic range, large x of m, and small quantization error, the only way to do that is to do what? Increase b. I have lots of number of bits per your register. Don't do 8 bits, but do 16. But that's an obvious solution that we all knew about before, but that's something we want to avoid. In reality, you want to implement everything with as few number of bits in your registers as possible. You want to stick to an 8-bit or 16-bit arithmetic system and not have to blow 32 bits or 64 bits to do that. So what I want to maybe write down as an upshot of all this discussion is that there is a sort of a trade-off, if you will, between quantization error and dynamic range for a given number of bits. B. Okay? And what do I mean? What I mean is that to minimize overflow, again, with fixed number of bits, I put it in parentheses, but it should be clear, with fixed number of bits, we must increase, in some sense, x sub m. But then that makes delta to go up, and then that makes the error to go up. That means quantization error went up. Okay? So this is what I mean, there's a trade-off. That means there's a trade-off between dynamic range and quantization error. Again, this is all with fixed number of bits. With fixed number of bits. And the only way to get around that, to improve that trade-off, is just jack up more bits. But the more bits you have, the more hardware inefficient you become. So before sort of moving on to now slightly different sort of a thing, talk about this, cascade implementation and how the quantization stuff works there, I just want to make one more sort of a side comment. I think it's an interesting property, and it's a little bit counterintuitive, but you should be aware of it. And the property has to do with 2's complement, arithmetic number system. And it goes as follows. Suppose you're adding 10 numbers or n numbers in 2's complement, and you know the final answer is not going to overflow. It's going to be in your plus x of m minus x of m range. And what this property tells you is that even if in the intermediate values, when you're adding up these 10 numbers, you overflow, the final answer is still correct. And that's a property of a 2's complement, and it has to do with this picture that I just talked to you about. So it says that as long if you're adding a whole lot of numbers, as long as the final value is in the correct range and didn't overflow, even if you overflew in the intermediate values, your final answer is still correct. Okay. So I'm not going to pursue this further and use it in any way, but I think it's an interesting property that you should probably be aware of. Okay, so let me just quickly write that down so we have a sort of a record of it. So for 2's complement, and why is that an important thing? Let me just dwell on it just a little bit. It's good for implementation purposes. You can let the thing overflow, but as long as you're sure that after you take, let's say, the inverse DCT in your video coding system, the number is between 0 and 256, you can afford to have all these overflows happening in between. So for 2's complement, if the sum of n numbers doesn't overflow, then the result is correct, even if intermediate results overflow. So that's one advantage of using this natural overflow thing that I talked about, over saturating and clipping things. Okay. Okay, so the next thing I want to talk about is quantization in implementing systems, in particular implementing FIR and IR systems. And I want to start with figure 6.39, just so that you can see these various sources of error that I was just talking about earlier. Can you zoom in on the top part? Okay. So here what you have is a continuous time signal coming in. Then we do continuous to discrete conversion at sampling rate of t. You get this discrete time sequence x of n. And here's our famous h of z filter, 1 over 1 minus a z inverse. Right? The thing comes in, you delay it, multiply by a, you add it. Then you get y of n, and then you convert it from discrete time to continuous time, and you get the continuous value, y sub c of t, right? And real life, if I wanted to, the continuous to discrete time conversion doesn't have infinite precision. The multiplication by a doesn't have infinite precision. The addition here doesn't have infinite precision, and the d to c doesn't have an infinite precision either. So if I wanted to add all the quantizations that occurred in this really simple system, I can do it like this. So the continuous time signal comes in. This is an ideal continuous to discrete time conversion. And then I put this quantization because this is the quantization that is here because of this guy. This quantization box is here because I'm multiplying by a. The a itself has been quantized. And also I'm multiplying by a quantized number. And this thing is here because when I add these two things, there's a quantization going on. And then there's quantization going on because of the way I convert back. So this is sort of called the nonlinear model of this whole thing. In other words, this gets quantized, this value gets quantized, this value gets quantized, and there's quantization here also. So this is the nonlinear model. Now, what is the simplest way of analyzing anything nonlinear? You linearize it because it's too difficult to analyze anything that's nonlinear. And how do you linearize quantizers? You can only linearize quantizers under certain assumptions and conditions. And a lot of times there's papers and after papers that have been published in the literature that show you how much of a mistake it is to linearize quantization error under certain conditions. So there's lots of papers that talk about that. Nevertheless, we do that. We linearize this quantizer. And what I mean is we replace each quantizer by an error source getting added. It's an additive model for quantization, additive noise model for quantization. So E sub I of n gets added here, E sub A of n gets added here, E sub O of n gets added here, and out comes here. So this is the linearized model of that. Yeah.
Why is the last quantization block after the fan out?
You mean here?
Right.
You're saying there should be one here. Well, if you assume that there was no overflow, when you add two fixed point numbers, you don't get any errors, right? The only error, when you add fixed point numbers, the only time you get an error is if the thing exceeded.
But isn't there still a quantization error?
No, if I add two fixed point numbers, I get another fixed point number and no error got introduced, right? Except if it overflows, then then you either have to do the natural overflow or the saturation, then you're adding error. But if it doesn't overflow, then you don't get any error. Now when you multiply two b-bit numbers, you get 2b. When you multiply two b-bit numbers, you get 2 b-bit numbers. That's a hard sentence to say. And then you have to truncate that to 2 b-bits to b-bits. Oh. And that causes error. So multiplication in fixed point introduces errors because you truncate. You want to have the final answer in b-bits, but additions doesn't. Okay, so what I'm going to talk about just really quickly now is the effects of coefficient quantization. Okay, when I have a filter like, so effects of coefficient quantization. So when I implement a system like this, there's two sources. There's the fact that my coefficient isn't the exact coefficient I wanted. I had to quantize it, and then there's the round-off errors of the arithmetic that I have to worry about. So effects of and today I'm going to start talking about effects of coefficient quantization more than anything else. Right? So what do I mean by that? Well, I have an h of z, let's say an IIR filter that has two polynomials, sum of two polynomials, you know, b sub k, z to the minus k in the numerator, a sub k, z to the minus k in the denominator, and I've designed this. You still don't know how to design this, so it's okay. We'll talk about that later, but in a painstaking way, I've finally designed it. First I designed my algorithms, then my algorithm said I need an IIR filter, then I designed the IIR filter, and now I have to implement it. Now when I do that, the quantized value of this thing, one source of error is that my coefficients are quantized. So I put bk hat and ak hat. Okay? And the thing that you worry about here is that, okay, so you can implement this IIR filter in various forms, direct form 1 and 2 and cascade and parallel. And one of you asked me before, what's the difference between these? Why are we talking about all these things? And the answer is direct form 1 and 2 are highly sensitive to coefficient quantizations. Why? Well, think of the denominator. This has a whole bunch of poles, right? And this corresponds, the numerator is another polynomial that has a whole bunch of zeros. Now, we already talked about the fact that some problems are ill-conditioned, right? We already talked about the fact that finding the roots of a polynomial is an ill-conditioned problem, which means that if you perturb the coefficients of a polynomial a little bit, the roots change a lot. This is particularly true if the roots are clustered together. That becomes even more ill-conditioned. And so that manifests itself directly into this quantization problem. A sub k's are the actual coefficients, unquantized, real-valued coefficients. By the time I quantize them, what have I done? I've perturbed the coefficients just a little bit. By how much? By quantization error, by the act of quantizing it. And now what has happened is the poles of this system have, because changing the coefficients of a high-order polynomial makes the roots change a lot, I have changed the poles a lot. And in fact, when I do direct 1 and direct 2 implementations, in particular direct 2 implementations, essentially, I didn't bring the papers with me, but essentially what you have is a flow graph like this that goes on forever, and all that there is in it is the coefficients on the flow graph are nothing but these coefficients of these polynomials. And therefore, in the process of putting these, you change the roots quite a bit. On the other hand, in cascade structure, the coefficients of your polynomials in your flow graphs, you might have second-order flow graphs that correspond to direct 2, but in cascade, there's a cascade of those. So, and you're directly dealing with the roots of the polynomial itself, and so if one root of a polynomial changes, it doesn't affect the root of the other polynomial. There's no interaction between these cascade structures. And therefore, in cascade structure, you get a lot less quantization effects than you would in direct form 1 and direct form 2. Here, one coefficient changes. Let's say the coefficient here, a sub 1 changes. It affects all the roots of this polynomial. It moves all the poles, and therefore all the roots of this polynomial. Whereas in cascade, the effect is much more localized. A coefficient changes, only that root changes. It doesn't propagate the effect to all the other roots and all the other poles. And just to see an example of this in action, let's say you've designed a elliptic IIR filter, and we'll talk about what that is. And these are it's a 12th order elliptic filter, so these are the A sub k's and B sub k's for it. Okay? These are unquantized. And if you were to plot zoom out, please. Yeah. So if you were to plot the log magnitude for the unquantized thing, it looks something like this. Okay? And instead of log magnitude, which is in dB, you can also plot the amplitude of this thing in the passband from 0.3 to 0.4. Can you show these two things simultaneously? Great. So this is the log magnitude from 0 to pi, and in this blown up portion from here, from 0.3 pi to 0.4 pi, which is here, we're showing, what this thing exceeded 0, so we're sort of blowing that up, showing it down here. Now, what happens is that if you quantize for cascade structure, if you quantize the coefficient to 16 bits, in this passband region, this is what you get, which is a pretty faithful representation or replication of unquantized. This is for cascade for 16 bits. Furthermore, if you do it with parallel with 16 bits, you get this, which is a pretty faithful representation of that. Nothing much changed. On the other hand, if you go to direct form 2 and do 16-bit coefficients, this is what you get for log magnitude rather than that. Compare this with that. So 16-bit quantization coefficients for direct form 1 really messed up your frequency response in a sort of a big way. Right? Here, this thing it exceeds 0 dB. It hits 0 dB and it looks something like that. Here, in this range, it doesn't even hit minus 20 dB. It doesn't even reach 0 dB. So you've messed up your log dB, your log magnitude thing in a sort of a major way by using 16 bits of coefficient quantization in direct form 2, whereas in cascade and parallel, nothing happens. And it has to do with the fact that when you change one coefficient in direct form 1, it affects all the poles. Or if you change one coefficient in the numerator, it affects all the zeros. Whereas in cascade or parallel, in particular in cascade, it's easier to imagine when you change one coefficient in one of cascade is a cascade of a bunch of second order terms, right? If you change one thing, it doesn't affect other poles or other zeros, and so the quantization effects are much more local. I think I'm going to stop now. I do want you to pick up the lab. Actually, let me just pass in order not to cause chaos, I'll just pass some at this end, some at this end, while you guys are seated, so that just pass it along. Pass it. This end, this end. I'll go to the other end of the class too. Start from this end. Start from this end. Everybody should get it real rapidly. And on your way out, pick up the solution. The solutions are now posted on the web anyway. This one, okay, sure. And pick up your graded homeworks as well. So this is the solution, and that's the graded homework. And if you want the lab, it's also, I put some here as well.
in order to do all the bias, so we can calculate what's the current flow through this branch, right?